Okay, can you hear me well? Welcome everybody. My name is Dominik Lewy, and today I will present a lecture on transfer learning in neural networks. A word of introduction: I work at Lingaro. It's for me mainly data science company. There I'm a lead data scientist responsible for computer vision area. I additionally pursue my PhD degree from Warsaw University of Technology, where I also focus on convolutional neural networks and applications to computer vision. Okay, so what are we going to discuss today? First of all, I would like to do a quick introduction into convolutional neural networks and autoencoders, in case you do not know what those terms are. Then I will talk about the core of the presentation, so single task and multitask models, as well as transfer learning. This will end the theoretical part. And then I will try to jump into Jupyter notebooks to show you some codes, how to work with convolutional neural networks, what are the ways we can use transfer learning to our advantage on your projects. Okay, so hands up, who knows what convolutional neural networks are? A lot of people, still some hands down. So I would summarize these convolutional neural networks to, for me, basically two terms. Convolutional layers, which are layers responsible for extracting information from the image. So some filters trying to extract pattern, high-level features. And to pooling, which are operations aimed at reducing the dimensionality of our image, so fastening our algorithms and making the data smaller for us to process. I have a neat example on how to apply convolutions, but I don't know how it's going to work, so I will make just one try. Okay, so right here, you also can see the Excel. Perfect. So here we have an image of an X, and we are going to apply a filter that is going to find some pattern. And this is exactly the convolutional operation. So let's, for example, try to find an X. Here I'm trying to input the filter. Okay, so this is the filter that is convolving with our image. It's simulated in Excel here. So this will be the result of our fully trained convolutional neural network. And this gives us an activation map, which shows us whether this pattern appears on the image or not. So this is like summary of the convolution. And we can have a lot of filters in our nets to extract many features. So not only crosses, but also other lines and stuff. And pooling, it's the dimensionality reduction. This is the last part. So basically here we are taking the maximum value of our activation map, which tells us whether this feature appeared in the image or not. Irrespective, and it's not it's not showing the position exactly, simply whether the feature appeared or not. Okay, coming back to the presentation. Okay, the same question goes for autoencoders. Who knows autoencoders? Okay, still some hands down. For me, autoencoders are similar to principal component analysis, which is a dimensionality reduction technique. So basically, we try to reduce the volume of our data and only select the most important information and try to present it in a smaller number of features. But here the main difference is that autoencoders can use the benefits of deep learning. So they can present nonlinear relations. So they encode our data better. Okay. First of all, single task approach. We have one data source and one net that is responsible for one job. So for example, one net categorizes the images, other net labels them, and so on. We can move it a step further if we have a multitask approach, so one net that does more than one job. And to put it into an example, first of all, they developed categorization networks. So for example, we could tell that on the image there is a dog. This was one task. After that, they developed localization networks that also pinpointed where the dog exactly is. So the network gave not only the label, but also the exact position of the dog in the image. But if we moved it even a step further, there are a lot of problems that have multiple channels. Movies are a great example here, because like one movie is composed of 3 channels, of video, audio, and the text, and it forms a cohesive, it forms the full image. And we could try to use this information to make our models better by combining those different types of information. But you probably already see what's the problem here. We have data sets that are completely different. So how to combine video, sound, and text. Here, with help comes something like a multimodal approach and finding the common representation. So multimodal autoencoders. Those are autoencoders that can help us transform all of these different types of information into the same common space, which we can then fit into our neural networks. And why this might be important for us? First, we might want to reconstruct a missing channel. So, for example, reconstruct subtitles from the image and from the audio. Or transfer learning, if we wanted to make a censoring engines which would beep out the false words. We could use the text in order to help to solve this task. Or improving view performance when we have multiple channels. This is commonly used in machine translation, for example, by Google. I will tell that at the end of the presentation. Okay, and at last, transfer learning. For me, I would sum up it like that it's using knowledge and wisdom of millions of images to help us solve our problem. And it basically sums up to using the architecture and weights trained on different data set and applying those to our problem to help it solve it better and achieve higher accuracy. I will tell about different types of transfer learning using a simple example. This is not yet transfer learning, but I will use it as a starting point. Here I'm presenting architecture of AlexNet, one of the first high-performing neural networks, convolutional neural networks. I divided those layers into 2 groups. The first, the one on the left, is the convolutional layers. And I would say that those layers are responsible for extracting features. So they do not actually solve the problem, but they help us understand the image so that we can, thanks to those features derived from those layers, then solve it using fully convolutional layers. And the layers on the right are those that are responsible for solving our problem. Those are fully connected layers that solve our problem. Okay, so now first way we can apply transfer learning. We could use this architecture and the weights trained, for example, on ImageNet. It's one of the common data sets used in computer vision. And we could use those features as they are, without changing anything, and simply try to solve our problem and train only the problem-specific layers. Then we would be using this as a fixed feature extractor. So we are not changing the features. So, for example, a feature could be a nose, an eye, a wheel of a car, and so on. And we are only trying to solve a problem using those features. But we could also move a step further and try to fine-tune also those layers in hope that we can find some particularities of our data. Okay, So we know a lot of different approaches, but what's here for you? Which one should you use? Advantages and the disadvantages. If we use the black box approach, we do not need any knowledge, because we simply take an architecture that is already ready, it is trained, so the weights are already present, but it has very limited usage, because we can only solve the same problem that the author of the network solved, and we do not have any impact over the input size or over the architecture. So, for example, most of the architectures are trained for common object detection. If we were to work with satellite images of high quality, it would be useless for us. Then feature extractor and fine-tuning, those are the transfer learning approaches. We can use information that it's extracted from millions of photos. This is good. But still, the possibilities of changing the architecture are quite limited, because we cannot impact, for example, the convolutional layers and the architecture. And we can, of course, train something from scratch, so design our own architecture and simply use only our data. Okay, and the takeaways here. Which approach should you use if you were to do a project of your own? And I divided this into a matrix, where one of the dimensions is the size of the data set that you have, and the other is the similarity to common data sets that are already available. So if you have a small data set that is similar to, for example, common object detections, you can try using a fixed feature extractor, because the problem is similar and you do not have so much data to try to impact the convolutional layers. On the other hand, if your data set is quite huge, you can try to use fine-tuning in order to extract, the peculiarities of your own data. And in case that your data set is not that similar to what's already available, there are not much options. If you have a large data set, you are lucky enough, you can train something of your own. If you have a small data set, probably try gathering more data. Okay, and for the example part, I will sit down. So, to the codes. Okay, you should be supposed to see a Jupyter notebook, and it's over there. Okay, first of all, I didn't want to work with MNIST, so I designed something of my own. But I am lazy, so I didn't want to label data manually, so I used something that was already available. I use HAR cascades, which is an old way to work with the data to label the data for me. I basically downloaded a bunch of images of politicians from the web, and I asked this traditional classifier to detect faces for me. Quick word on how HAR cascade work. It's a traditional way, so features are extracted somehow manually, not trained. We have a bunch of predefined features, which is the sum of squares under the white bracket divided by the one under the black square. And we have like 180,000 of those. We train which one are the best by using AdaBoost training. And in order to speed the classification process, we simply make a cascade of those. And this is actually a nice touch, because we only check the most relevant feature at the beginning. And if the image does not pass the first check, we do not check any other. So it speeds up the detection process. Okay, I wrote a couple of functions here. As I said, this is something that that's something that's already available, and it's from the OpenCV library. Here I defined a function for finding faces. I don't know it's big enough. So yeah, basically I am using a already trained Haar cascade classifier to find faces. Yeah, I'm declaring it, and the input needs to be in grayscale, so there's a transformation. There is a similar function which also returns the grayscale image for the presentation purpose, and the function which plays with the parameters, so it basically runs the algorithm a couple of times with different settings. And here we have a presentation of how it works. So an input was the put-in photo, and at different parameters we have the detections. Mean neighbors is a parameter telling the algorithm how many boxes need to agree in order for the algorithm to say that this is the face. And the scale factor is how much we change the scale of the image at each step. And it allows us to discover faces at different scales. I will be making the notebooks available, and I will show the GitHub repo at the end, so I will skip some parts. Here we have the example of what the input looks like and what's the output on the Obama case. And basically what we wanted to do is extract the position of the image so we can work with only the face. And here we are iterating over folders. Each folder is contains images of only one person, and we are selecting face for each file. So it's basically a loop over our entire data set. So we already have the faces extracted. Here is a summary table showing how many faces were found for each politician. So for example, in case of Cameron photos, we found 0 faces for 9 images. This is, of course, a mistake of the algorithm because all of those images had faces, but we have quite a lot of images where faces were found. And here are some results. And here I wrote a function to visualize those. We can select how many faces we want and to see in the image and how many images to show. And examples. Here we have Cameron a couple of times. Okay, so basically this was data creation. Now let's go to the autoencoder part. Here we will do both two things. First, we will train an autoencoder on different data set, and we will try to apply it to the data set that we just created. This will be the example of using like off-the-shelf solution. So the first one I described in the presentation. All the libraries needed. I will be using Keras for the autoencoder part. And yeah, we are training an autoencoder on the labeled faces in the wild data set, which are 32 by 32, 3 color channels. To better train the autoencoder, we will be transforming the input, centering the pixel values. So here are the example of the input, the autoencoder input, and a couple of examples of how the faces look in this data set. Here is a helper function for visualization. It presents the original image, the source code, so the vector to which we are going to encode each image, and the reconstruction, and the clue of the presentation, so the autoencoder part, where we use a mixture of convolution and pooling layers, trying to reduce the dimension of the image, and at the same time increasing the number of features. 32, 64, so the number of filters. After that, we are flattening everything and adding one fully connected layer, the size of the code size, so the number of features to which we want to encode the image. And this was the encoder, and the decoder, so the one that reconstructs the image, is basically reverse. So we are reducing the number of features and increasing the image size by using conv to detranspose. It's not exactly deconvolution, but if you are familiar with this concept, you know why. Yeah, it's tricky because I don't want to get into that. Here we are building the network and showing the summary. So how the architecture look like, how many parameters are there. And after that, we have the training part. I will not be running this right now. It takes around an hour to train. I already saved the weights. I will only show you the results. So reconstruction MSE and some images that were like original, coded to 32 features. No, sorry, 30, and the reconstructed image. We can see that the quality is quite okay. We did not lose much details. And the reconstruction MSE, we will use it as a reference point for further experiments. Okay, so we have trained autoencoder. We have our faces. Let's put our faces into this autoencoder. So I'm going to skip this part of the code which generates the data again. Here is an example of like the process we went through. Whole image, cropped face image detected by the HAR feature, HAR cascade classifier, and the resized image because we needed to resize each face exactly to the input size of our autoencoder. And as our autoencoder was trained on images 32 by 32, each of our faces needs to be like resized to this image. Even if we had a high quality face, like say 100 by 100, we would need to lose this quality because we have an architecture that is fixed. Okay, here are the transformed images, just as for the previous data set, and we are doing the same transformations because we need to simulate the same pre-processing as we did for the initial autoencoder, and that's like, yeah, the results. The reconstruction MSE much higher, and is also probably seen in the quality of the image. We can see that much of the details were lost. The faces do not look fine for me. Okay, so we can see that it did not work well. We used an off-the-shelf model. So let's try to build something of our own to see if we can improve this result. So first of all, if we are building something of our own, we do not need to limit ourselves to the architecture that is already known. We can have a bigger input size. Let's say 48 by 48. Why not? So we have at the input images of higher quality. Then we will be building a network that is the same, almost the same in architecture, but we will increase the code size. So the number of features that we are using to encode our image to 100. This is, yeah, to 100 because we want to convey more information. And here are the results. So much lower reconstruction MSE, and I would say that those faces have more detail than the previous ones. It's still not perfect, but I would say it's better. Okay, and the last thing I wanted to show you today is an convolutional neural network trained on those images with faces and tested on, if I remember correctly, COCO dataset, so common objects in context. From the start, I will say that this is not entirely my notebook. I didn't want to rewrite the wheel from scratch, so for visualization purpose, I used the object detection demo from TensorFlow Vision API. I only changed some things. I wanted to add a reference point, so the HAR cascade classifier, and I inputted my own detector, the one that was trained on the data created here, that is able to detect faces. So some environment setup. Here I declare my own object detection, the face detector, loading it into memory, loading the labels map, using the data set that we created in the first Jupyter notebook. Here is the function for running inference, the convolutional neural network, and the part I added using HAR features to extract faces, and like a comparison, trying to run both algorithms on the same images. So one of the examples, we can see that neither of the algorithms work perfectly, but and one important thing, red is HAR, green is SSD, so the fine-tuned convolutional neural network. Some algorithms were able to find different faces. Some faces were not found by either algorithm. Okay, coming back to the presentation. Extend. Okay, so a quick summary. As for HAR cascade, we use those for initial dataset creation. This algorithm made some mistakes. Sometimes it detected nothing. Mostly it was correct, but sometimes when predicting more than one face, incorrect. We trained 2 autoencoders, one for different dataset, and used it as a black box off-the-shelf model, which gave us poor performance. And we trained a custom one, which gave us lower error and better results. And it proved that doing something from scratch has more flexibility and can give us better result if we have data and time. And we did not fine-tune, but we showed results of a fine-tuning of a convolutional neural networks for the problem of detecting faces. In the abstract of the conference, I also told you that I will be telling something about other areas, for example, machine translation. The time is scarce. We are running out of time, so I will only mention one article and why it's important. In machine translation, Google, maybe not quite recently, but somewhere along the time, introduced something called zero-shot translation. It uses the concept of training pairs of languages through an autoencoder, which basically creates an intermediate layer. They call it an interlingua. So this is like a language known to the algorithm, which translates one language to this language known to them, and from that language that does the translation to another language. Why is it important? Because it greatly reduces the complexity of this problem. From this slide, you can see that if we want to do direct translations from each pair of the languages, we have a lot of combinations, and if we go through an intermediate language, we only train pairs. Here is a reference for this article, if you are interested. That's everything for today. I would like to invite you to Lingaro stand, and all the codes that I showed are available on the GitHub, the Lingaro Data Science. Thank you very much.
Hello. First of all, thank you for the presentation. This part of using the first layers of, for example, ImageNet is something that has become very common in transfer learning, but other areas that are not image recognition tend to not have such an easy way to do things. More recent techniques such as model agnostic meta learning sort of allow for alternatives that not involve necessarily image classification. But I wanted to know if you were aware of any of these more recent transfer learning techniques that allow you to achieve similar success not on image recognition but other tasks more related to tabular data, for example. If there's any, what would your recommendations if I was applying this on tabular data rather than just image recognition? Thank you.
Okay, correct me if I'm wrong. Don't lose the mic yet. Are you talking about unsupervised pre-training?
No, I'm talking about supervised learning. For example, few shot classification, for example.
Okay, I did not touch that part, so I'm not able to comment on this one.
Okay. Thank you so much.
You have to hit a bit harder.
Oh, okay, sorry. Okay, thanks for the presentation. I got a comment maybe or a question, because you showed that if you encode, I mean, okay, at the beginning you started with comparing somehow the PCA with autoencoding, which I basically don't agree that this is the same, but I mean the similar. But nevertheless, you showed that if you encode a phase in a 30 kind of unit space, you get lower results than if you encode on 100 unit space. And have you maybe made experiments regarding the accuracy of the reconstruction with regard of the units? Because basically, if you if you speak about PCA, if you just take two components, you get lower resolution than if you could extract 10 principal components. And basically the same. If you use 30 units, you get lower, kind of more information loss than if you use 100. So have you compared your kind of made from the scratch model in 30 units as you use the auto-shelf or not?
Okay, so to your comments, I use this PCA analogy because it helps understand what's the purpose of this exercise. And as PCA reaches the dimensionality, autoencoders also can do that, but on a higher level because of the non-linearities introduced, so they can model more complex data. And on the other comment, I wanted to show that the 32 is a limitation of the existing off-the-shelf product. So if we get this, we cannot, we basically cannot get better results because this is already available to us as it is. And if we try to build something of our own, we can make the error lower. But I did not check if the 100 would give the better performance there. Yeah, this was like a simulation of off-the-shelf, because I did train it, but for the purpose of the presentation, I assumed this is off-the-shelf.